All right. Oops. So welcome everyone to this tutorial on dynamic data race prediction. Can you hear me? Please react if so.
I can see you.
Okay, that's great. So please be patient for a couple of more minutes as we wait more people to join. We should have already started broadcasting live on YouTube, and I will also record this tutorial. So if you don't want your face to appear, please keep your camera off at all times. Otherwise, you're welcome to switch your cameras on as well.
So are my slides visible?
Your slides are visible, Monk, yes.
Okay.
All right, so I think I'm done as an administrator. I will switch off my sound and my microphone, and I will let you, Monk, start in a couple of minutes.
Yeah, let me wait for one more minute and then I can start.
Sure, yes.
Okay, so I think it's about time. So let me get started. I am Umang Mathur, and I'll be co-presenting this tutorial with Andreas Pavlogiannis, who is an assistant professor at the university at Aarhus University, and I am a soon-to-graduate student at the University of Illinois at Urbana-Champaign. And we will be talking about the fundamentals, theory, and practice behind what we call dynamic data race prediction. Before I get started, let me remind you that this tutorial is going to be recorded via its Zoom meeting, which means that if you do not want to show up in the recording, I request you to please switch your cameras off. Also, this tutorial is also going to be live streamed on the ACM Plans YouTube channel, so you can watch it offline again. This tutorial is structured so that there are multiple sections and there are breaks in between two sections. So I request that outside of these Q&A sessions, please mute yourself on Zoom. Also, if you have an urgent question, feel free to use the raise hand feature in Zoom. So also we'll be monitoring the Clouder chat for questions if you have. The Zoom chat is disabled. Yeah, finally, the materials for this tutorial are available on the tutorials webpage on the POPL website. so you can access them even after the tutorial. With that, um, let me get started. So concurrency today is so ubiquitous, it can be found in every modern real world software, be it web browsers or operating systems that you use on a daily basis. But and also these concurrency has served as the backbone of big data and AI revolutions, and it will not be an underestimation to say that concurrency has been foundational to these revolutions. But again, it is not a surprise to say if I say that writing concurrent programs is a challenging task, and that's because there is non-determinism in these programs, and when programmers have to reason about the correctness of their programs, they have to look at a large interleaving space, and that is cumbersome and also error prone. And as a result, concurrency bugs like data races and deadlocks routinely manifest in production level software despite all sorts of rigorous testing efforts. And often concurrency bugs have led to very severe outcomes in the past. So this tutorial is about detecting concurrency bugs, and we're going to be looking at dynamic analysis for detecting concurrency bugs. Uh, in dynamic analysis, you do not analyze the source code of the program, but in fact, you let the program run for a while and record the execution and try to see if you can infer the presence or absence of bugs from this execution. So when we talk about dynamic analysis for detecting bugs, there are three desirable properties for any such analysis. The first is scalability, specifically for detecting concurrency bugs, because we're going to be looking at real world software like web browsers or web servers, which can routinely generate billions of events even for a short duration of their execution. The next desirable properties is soundness, which means that your analysis does not report any false positives. And of course, that is desirable because these executions are large, and when your tool reports false positives, then you have to manually confirm each bug report that your analysis reports, and that again is cumbersome. Finally, what we want is that your analysis has non-trivial capability for detecting bugs, or what we say, it has high prediction power, so that it does not miss a lot of bugs. And in this tutorial, we're going to be looking at some foundations of dynamic data race detection, with the focus on the three desirable properties that I talked about. And then we're going to look at some recent algorithmic advances in effective race detection. And finally, we're going to look at some fundamental limits in dynamic detection of data races. So with that, let me get started with the main content of the talk. But before I go into any results, let me talk about some preliminary notations that will be useful for the entire talk. So I'm going to be talking about concurrent programs. So these are Java-like concurrent programs that I've shown on the left. These programs have threads. Threads have local memory, so they can read and write to local variables. And threads can also communicate with each other using shared memory. Also, these programs can have synchronization constructs like locks that let you implement mutual exclusion. And finally, we're going to be assuming that these programs run on what is called the sequentially consistent memory model. And what that means is something that I'm going to talk about in the next slide. So when you have a sequentially consistent memory model, executions of your programs are essentially sequences of events. So on the right, I have an example of the execution, which is a sequence of 8 events. Every event tells you what is the thread that performs that event and what is the operation that was performed in that event. So for example, event number 1 here, is performed by T1, and event number 4 is performed by the thread T2. Now, operations in these events can be either reads or writes to memory locations. So for example, if you look at event number 2, it is a read from the memory location X, and it is performed by T1. And similarly, if you look at the event number 7 performed by T2, that is a write to the memory location Y. You can also have operations on logs. So uh, so these operations are acquire of log L or release of log L, and similarly acquire and release in this other thread. And lastly, we want that these executions are well formed. And specifically in our context, it means that if you have two critical sections, so a critical section is demarcated by the acquisition and the release of a log, then if you have two critical sections, so here is one and the other is here, these two critical sections on the same log do not overlap in a well-formed execution. So it's in some sense a consistent execution. It behaves as expected in the programming language semantics. Okay, so with that, let's look at what is a data race. There are several informal or formal notations or notions of data races out there, and the specific definition that we're going to look at is the following. If you have an execution, then in that execution sigma, a pair of events E1, E2 is said to be a data race if two things happen. So first of all, that pair of events is conflicting, meaning that they access the same memory location. In this example, the common memory location is X. And secondly, not both of them are read accesses. So at least one of them is a write access. So E1 and E2 are conflicting. And the other thing that we want is that they're concurrent. And roughly this means that, if you look at your execution sigma, then that execution has a prefix pi in which these two events are simultaneously enabled. What this means is that, so we can look at this example and I'll tell you what that means. It means that if you look at that prefix E1, E2 here, pi, then that prefix, right after that prefix, you can execute both E1 as well as E2. So here I can execute E3 right after this prefix because all prior events in T1 have been scheduled in that prefix. Similarly, I can also schedule E4 right after that prefix because in fact, there are no prior events in the thread of E2, which is the thread T2. So, an execution has a data race even E2 if even E2 is a conflicting pair of events and they're also simultaneously enabled in a prefix. So they're concurrent in that sense. Now, having defined data races this way, one obvious way to detect data races dynamically is to basically execute a program and then check if it witnesses a data race. So that this check is pretty simple. You basically look at the execution in a one pass streaming fashion. But then there are problems with it. So let's look at this execution. The only pair of conflicting events is the read X here and the write X here. Okay, but based on our definition of data races, this is not a data race because they're not simultaneously enabled in any prefix here. Okay, the only prefix of relevance is the prefix containing E1, but E2 is not enabled because the write Z is yet to be performed. But if you look at this execution, which is very similar to the first execution on the left, this execution has a data race. Okay, these two events, conflicting events, are in fact next to each other. So they are simultaneously enabled or concurrent in the prefix E1, E2. So there is a data race here. But what is more important is that this is what we call a reordering of the original execution on the left. Or in other words, you can expose data races by reordering executions, and which means that even if the execution that you observed may not have a data race, you can infer the data race by reordering your execution which might have a data race. So this is a way to sort of expand your coverage when you're detecting data races. And that is also the principle behind predictive analysis, which is the theme of the entire talk. So, a natural question arises here, which is what sort of reorderings are really allowed? So let's look at this execution. And here, let's see if the right Y and the right Y here are a data race in this execution, or they can be reordered so that there is a data race between these two. Right now, there is none. So, the only way to sort of bring them in a data race is to reorder this execution so that this readx goes above the right Y. Okay. So if you try to reorder this readx above here, which is in the same thread as T2, but in between the right X and the right Y in T1. So if you try to reorder this execution so this readx appears somewhere in the middle here, then that reordering is in some sense okay. That is an okay reordering. But if you try to reorder this readx up above here, so in the same thread, but even above the right X in T1, then that is not an allowed reordering in some sense. And that could be because the underlying program that this execution is coming from could very well be this program. So this is a program with two threads, T1 and T2. In T1, you perform a write to X and a write to Y while acquiring a lock. And in T2, you perform a write to Y only after reading to X and only when the value of X is a particular value 42. So as you can see that the original observed execution is an execution of this program because you can first execute T1 entirely. And that means at the end of execution of T1, you will have the value 42 in X. And then, you can start executing T2, which means that you will first read the value 42, and then which means you will be entering this branch and you will be executing this write. Okay. But if you look at this kind of reordering, where you're pushing this read of X above the write of X, in terms of the source code, it corresponds to the fact that you're doing this read of X prior to writing this value 42, which means that the value that X reads is 0 because the initial value is 0. And then you will not even enter this branch. So you will not even execute the write of Y. Okay. So this means that there is this adversarial kind of program that might have executed this, but might not execute this reordering that you're trying to infer. So in that sense, this may not be a data race if you're trying to witness it using this reordering. So the bottom line is that when you do not have access to the source code, you have to be conservative, and you cannot infer a lot of reorderings. There are only some special reorderings that you have to look at. So the kind of reorderings that we are going to look at are governed by this principle, which is the following. So if you have an execution sigma, then if you're trying to infer this reordering sigma star from that execution sigma, then that reordering is allowed only if any program P that generates sigma can also generate sigma star. Okay, this is a way to do source agnostic analysis to collect all possible reorderings which are going to be allowed no matter what program the original execution came from. So, this is an intuitive principle, but how do you formalize this? While this is not the scope of this talk, but let me sort of give you a brief intuition on how this is done. You have to look at the semantics of the programming language and understand how a program leads to executions. And that means that you have to formalize the properties of different concurrent objects in your programs, like locks or shared memory or even threads. And then, in the context of the programs that we're looking at, we have to look at these two properties called local determinism and prefix closeness. And what the entire exercise yields is a concise definition that I'm going to talk about in a while. But before that, let me talk about some more notations that will be useful for the rest of the talk. So if you have an execution, if you have an execution of a concurrent program, then you denote by events sigma to be the set of events in that execution. By TO, we denote the thread order of that execution. So the thread order will order all the events in a given thread in the order in which they appeared in that execution. Any execution also tells you what is the reads from mapping for that execution. So in sequentially consistent executions, a read of a variable reads from the last write of the same variable. So for example, here the reads from of this event is the write x here because it's the last write above this read x, and similarly the reads from of this read of y here is the write y up above here. Okay, so every execution tells you what is the thread order and what's the reads from relation function. And with these two, you can also define this partial order called TRF, which is essentially a combination of the thread order as well as the orderings induced by the reads from mapping. So this is a partial order which will order all the events in a thread, and it additionally will also order the read after its corresponding reads from write. So with that, we are ready to define what we mean by an allowed reordering. We're going to be using this definition by Smaragdakis et al., which is called correct reordering. So if you have an execution sigma, then sigma star, which is just a sequence of events, is said to be correct reordering of sigma if the following things hold. So we of course first want that sigma star is a well-formed trace, which means that if you have two critical sections in the same lock, they do not overlap in sigma star. Additionally, we want that, sigma star does not have an event outside of the events of the original execution. Third, we want that sigma star, that the events of sigma star, that set is downward closed with respect to TRF, meaning that if you have any event E in this set, then any event which is thread order before this event is also in the set. And similarly, if you have a read event in the set, then its reads from, which is a write event, is also in the set. Also, we want that the sequence sigma star respects the original thread order. And we want that every read, in fact, sees the same last write as in the original execution. So what is the point of defining it this way? Well, intuitively, it basically means that if you have a correct reordering sigma star of sigma, then sigma star can, in fact, undergo the same control flow as sigma. Meaning that if there was a branch that your program took in sigma, then the same branch is going to be taken in sigma star because every read sees the same value, so it can very well take that branch. And so defining correct reorderings in this fashion ensures that any program that generates sigma can also generate any correct reordering of sigma. Okay, so coming back to the principle of DataRace prediction, if you have a sigma, if you have an observed execution sigma, you can reorder it so that you get a correct reordering and try to infer the presence of a data race from the correct reordering, and that way you can expand your coverage. So with that, let's define what are predictable data races. And I'm going to be using this example here. So a pair E1, E2 of events in your execution sigma, which is an observed execution, is said to be a predictable data race if, of course, they're conflicting. So read X and write X here are conflicting. And secondly, there is a correct reordering of this execution in which they are simultaneously enabled or in which they're concurrent. So this correct reordering in some sense has a data race, but the original observed execution has a predictable data race. And again, the principle behind predictable data races is that if you have a predictable data race in your execution, then that means any program that gave rise to this execution has a data race. It has an execution which witnesses the data race. Okay, so before we look at some techniques to predict data races, uh, let me tell you what the soundness and completeness here means. Uh, we're going to look at analysis, dynamic analysis, which have executions as inputs and they report a yes or no. So such an analysis is sound if whenever it says yes, that means that the input execution has a predictable data race. And such an analysis is complete if it always says yes whenever your input execution has a data race, meaning it does not miss any predictable data race inputs. Okay, so before we go on to sort of examples of predictive data race techniques, data race prediction techniques, let's look at some brief history uh, of data race detection. So data race detection has been there for over 4 decades now, and a lot of the advancements in the first 3 decades were centered around what is called as the happens before partial order, and we're going to look at it soon. Uh, and much of the focus was on scalability and performance and making race detection practical. Uh, and then starting from 2003 onwards, almost until a decade, a lot of techniques emerged which looked at more exhaustive ways to predict data races. And these were based on explicit or symbolic search. And finally, starting from 2012 onwards, there has been a surge in sort of smart or efficient ways to predict data races while still being better than happens before in terms of precision or predictive power. So we're going to look at some of these in this talk, but let me look at some historical techniques and let me give you an intuition of what they were really doing. So let's first look at eraser. So eraser was a tool which was based on this lock-set principle, which roughly says that in your execution, if you have two events which are protected by a common lock, then they're not going to be concurrent in any correct reordering. Okay, so that means they cannot be in a data race. They cannot be a predictable data race. So for example, if you look at this execution here, the right X and the right X here are protected by the same lock L, and therefore they cannot be a data race. So you know this principle detects data races only when it finds only when it finds a variable that is not protected by a common lock. But as you can see, this is an unsound principle. If you detect data races using this principle, you will report false positives. An example is here, where the right Y and the right Y are not protected by a common lock. So eraser will report it as a race, but it is not a data race because there is no correct reordering that can concurrently schedule them. Uh, let's look at the next set of techniques, or enumeration-based techniques, which are based on this principle that data race prediction is in fact a problem in the NP class, and that's because you can guess a sequence of events and check if it is the correct reordering that has a race. Okay, so a lot of techniques in fact exactly do this. They enumerate all possible sequences of events and check if they are correct reordering and have a data race. So as you can see, these techniques will run in exponential time in the size of the trace, in the size of the observed trace. Uh, there are some other techniques that in fact do this using a constraint solver. So they encode this condition that there is a correct reordering with the race as a SAT or an SMT constraint and ship it to a SAT solver. And as you can see, that can also take exponential time in the worst case. So while these techniques are sound and complete, they will always report a race whenever there is one, and they will not report false positives. But then because of their exponential running time, they do not often scale. Next is a popular technique based on this partial order called happens before. Happens before was in fact first given by Lamport. So in the context of data race detection, happens before is defined as follows. So it's a partial order on the set of events of your execution, such that all the events in the same thread are ordered by this partial order. And secondly, if you have two critical sections on the same lock, then they're ordered in the order in which they appear. So for example, here, uh, I have two critical sections on L1, namely one here and one in T2. And the release of the first critical section is going to be ordered by happens before the acquire of the second critical section. Similarly, I will have an happens before edge from this release to this acquire on the same lock. So happens before will transitively order all these events and also events in the same thread. So we have defined happens before. How do we detect data races using happens before? Well, that's a very simple principle. You basically have to look for events, for conflicting events that are unordered by this partial order. So an HB race is a pair of events such that neither E1 is before E2 according to HB, nor E2 is before E1 according to HB. So they're unordered by HB. And now the soundness guarantee for happens before says that if your execution has an HB race, then that execution also has a predictable data race. There is also a very simple algorithm that runs in linear times and uses vector clock for happens before, and that is the main reason why happens before is very popular and is implemented in most commercial race detectors. It runs in linear time and it is sound. Okay, with that, let's look at. Let me focus on the predictive power of happens before. If you look at this execution here, this execution has two conflicting events, and happens before will order this release before this acquire, and therefore transitively it will order all these events like this, which means E1 will be ordered before E6 according to happens before, or in other words, they are unordered by happens before, so there is no HB race here, and happens before will not detect a data race. But this execution is a correct reordering of this execution on the left. And this correct reordering, in fact, witnesses the data race between these two events. Which means that there was a predictable data race in the first execution, which happens before misses. And so it's fair to say that happens before is conservative. It orders all critical sections on the same log, even though that ordering does not mean anything at times. So happens before can miss very simple races like this, and therefore it has poor predictive power. So before I go into the next segment of the talk, let me summarize what we've seen already. Okay, so if you plot the techniques for predictive race detection based on their scalability and predictive power, happens before would lie somewhere here. Okay, it's very scalable. It has a linear time algorithm, but it's very limited in its predictive power. It only looks at linearizations of this happens before partial order, and therefore it can miss a lot of races. On the other hand, we have enumerative techniques, which basically enumerate either symbolically or explicitly all the correct reorderings and check them one by one. And these techniques run in exponential time, but they're both sound and complete. So they do not scale, but they have high predictive power in theory. And in this tutorial, we are going to be talking about techniques that have a good balance of of both predictive power as well as scalability. So we're going to look at techniques which have good running times as well as better predictive power than naive happens before. Okay, with that, let's look at the next segment, which is again a revisit on the soundness guarantee of happens before. Okay, so just to recall, what is the soundness guarantee of happens before? It says that if you have an HB race or a pair of events that are unordered by HB, then your execution has a predictable data race. It can be reordered to witness some data race. So let's look at this execution here. The happens before partial order here is just the thread order. So you order read X to write Y here, and then you order read Y to write X here. There are no cross-thread dependencies due to happens before because there are no locks. So that means that this two pair of events are unordered by happens before. And therefore, this execution has a data race. In fact, this is a data race, which is also witnessed in the same execution. They're in fact enabled in the prefix of E1. Okay, so they are also concurrent in the same execution. So that's a data race, which we already have seen here. But if you look at this pair of events, that is also an HB race. They're also unordered by happens before. Okay, but they are not a predictable data race. And again, that's because this could very well be the underlying program. Okay, so in thread T1, you are reading from X and then you're writing to Y. And in thread T2, you are writing to X only when you read a particular value from Y. Which means that if I try to schedule this read X and this write X concurrently, I will have to perform this read Y above this read X, above this write Y. And when I do that, I will not be reading the value 5 in Y, which means I will not even be executing this write to X. And in fact, I will not when I read Y, when I read a different value, I will in fact have a loop. So bottom line, this is not a predictable data race because you don't know the underlying program. The underlying program could very well be this, which disallows a correct reordering that exposes the data race. So the soundness guarantee of happens before is the following. Precisely, it says that if you have an HB race, then there is some predictable data race in your execution. It is not that any happens before race is a predictable data race. Okay, so what is the so let's try to characterize this happens before soundness guarantee in a much more precise sense. Okay, so you can make it precise by defining what is called a first happens before race. So roughly it means that a pair of events even E2 is a first happens before race if it is a happens before race such that there is no intervening race in it between it, meaning there is no other happens before race between the E1 and E2 of these two events. So for example, here write Y and read Y are the first race because there's no intervening write Y and read because there's no intervening happens before race. But if you look at this read X and write X, they're not a first race because they are intervened by this happens before race. Okay, so in fact the soundness guarantee of happens before more precisely is this: if you have a trace, then the first happens before race is a predictable data race. Okay, you cannot really talk a lot about other races just using happens before relation. Okay, not every happens before race is a predictable data race. In fact, checking if a HB race is predictable can be intractable. So what about other HB races? If we still want to detect them, how do we go about it? Well, we can go about it by looking at this partial order called SHP, or schedulable happens before. Okay, so it's again a partial order on the set of events on your execution, and it's also very similar to happens before. In fact, it is stronger than happens before. So it includes happen before, and on top of that, it also orders every read after the write that it observes. Okay, so if you look at this execution, this is an SHBH because this is also an HBH. And on top of that, you will also order a readx after the writex that it reads from. So SHB or schedulable happens before is essentially HB, except that you also add these edges that order uh, reads after their prior writes. And now, using this partial order, you can exactly characterize which HB races are witnessed uh, in an HB respecting correct reordering. So, an HB race even E2 is witnessed by a correct reordering that respects the happens before relation of the original execution, if and only if these two events are such that there is no intervening event uh, that is SHB between E1 and E2. Okay, so that's the so SHB precisely characterizes every it happens before race, which can be witnessed in a HB respecting correct reordering. Okay, so with that, let me talk about the algorithm. Well, the algorithm for SHB based race detection is very similar to that of happens before. Okay, it's a vector clock algorithm, and it runs in one pass streaming fashion. And in fact, it is so similar to happens before that existing race detectors can be very easily uh, tweaked so that they implement SHB and their sound beyond the first race. And just like HB, this algorithm runs in linear time and takes constant space. We implemented this algorithm in this tool called Rapid, which is available on GitHub, and we observed that SHB reports 50% fewer races, and the remaining 50% were in fact confirmed to be false positives. And SHB scales very well, even empirically. So this brings us to the first segment, to the end of the first segment of the talk, and let's take a break for 5 minutes before we enter the next segment.
All right, thank you, Mank. If there are any questions, people feel free to raise hand or unmute your microphone. If you'd rather write your question down, please use the Clouder as the Zoom chat is disabled.
Okay, so Parosh has a question. Parosh, if you're also on the Clouder app, you can post your question here. Otherwise, you can ask here.
I don't know, in fact. Yes, I think so. I came from there. So.
Okay. It's okay. You can ask here now that you're already unmuted.
Okay. Thank you. So my question is about when you, so it seems that you try to predict races by generating a new execution from one that you have got from the program.
That's right.
Then you demand that you preserve the order on events from the same thread, but also from the read from relation.
Yes.
But in principle, you could, instead of preserving the read from relation, you could read from any other write, which gives you the same value.
Yes,
and
that's right.
So what will happen in such a case?
That's right. So Parosh raises a good point, which is also something that Andreas is going to talk at the end of talk about at the end of his talk. He says that if you instead observe, if instead of only observing that you have a read event that reads from X, if you also observe values, which means that if I observe that read of that a read observes the value 5 from X, then in fact you can expand your coverage. You can expand the kind of correct reorderings that you're looking at by not forcing that you only read from the last write, but you can read from any write that writes the same value. So that's a good point. And where right now it's unclear that you can that there are efficient that existing methods that do prediction efficiently can be extended very easily to incorporate this principle. Okay, so I see one more chat question. what is the, okay, 50%. Okay, so Jens has a question. 50% fewer alarms sounds great. What are the absolute number of alarms for each trace that you looked at? I'm trying to gauge the amount of work to inspect the other 50%. Okay, so that's a good question. How did we confirm that these 50% were really false positives? And did we do it manually? Well, it turns out that you can do a lot of things to confirm something is a false positive. Okay, and again, to precisely what I mean by false positive is that there is no correct reordering in which that particular false positive is a predictable data race. So, the way we confirmed it is using a very simple analysis, which essentially says that if two events are ordered by this TRF relation, which is if they're either ordered by thread order or from this reach from relation, then they cannot be a predictable data race unless they're really next to each other. So this is how we confirmed all of these remaining 50%. It turns out that all of these could be confirmed. All these extra 50% could be confirmed using this simple analysis. But nevertheless, this does not mean that they cannot be a predictable data race in a totally different execution of the program. Okay, we're assuming we don't have access to the program, and that's the notion we're working with. So that should answer Jens's question. Okay. So if there are not many more questions, I can start in the next segment because I think I'm running over time. And there might not be enough time for Andreas. So yeah, let me do that. Let me start with the next segment of the talk. Okay, so next I'm going to be talking about weak causal precedence, which is a way to detect data races beyond happens before linearizations. Okay, so we've seen that happens before is conservative. Okay, here on the left, I have an example of a predictable data race, but happens before will order these two events and therefore not report a data race. So happens before is conservative because it orders all the critical sections on the same lock in the order in which they appear. And therefore, the space of correct reorderings that happens before is capable to reason about is essentially only the linearizations of that partial order. Okay, and while this is a good principle to have because it gives you linear time and it gives you soundness, at least until the first trace, it is not something that is a necessary principle. Okay, placing an ordering between two critical sections is not always reflective of any hard reorderings, because this execution here can very well be reordered to expose the data arrays. Okay, so and because of this this sort of conservativeness, you miss a lot of races, and all of this we have seen before. So the question that we want to answer here is, can we relax some HB orderings, or in other words, can we sort of come up with some other orderings, some other partial order that does not naively order critical sections like this? Well, if you naively try to remove orderings between critical sections, then that may give you infeasible reorderings and a potential for false positives. So, if you look at this execution, there is really no need to order these two critical sections. So this race on right X and right X can be exposed. But if you look at this execution, then in this execution, the two critical sections cannot be inverted. Okay, because if you try to invert the order of these two critical sections, then you will have to place the read X entirely above the right X. Okay, because critical sections cannot overlap. When you do that, your reads from mapping changes, and you're not even looking at a correct reordering. So not every pair of critical sections can be reordered. So which means that you might have to do a very careful analysis on when to reorder critical sections, and in fact that might be very expensive if you go full blown in a full blown manner. And that is where this new partial order that we have defined called WCP comes in. Okay, WCP essentially effectively identifies how to order or how to not order, when to not order critical sections. So with that, let me define this partial order WCP. So as with HP, it's defined using these rules. So WCP, or what we call strict WCP here. So it's a transitive order. It's the smallest transitive order such that orders events as follows. Okay. So the first rule says that if you have two critical sections on the same log, and the first critical section, and both of these critical sections contain conflicting events. So for example, here there's a right X and here there's a right X. These are conflicting and they're in the same, in the critical sections of the same log. If that happens, then you order the release of the first critical section before the second conflicting event. Okay. So it's defined in a very peculiar fashion, and I will probably not discuss why you define it like this and not by ordering release to acquire. And the short answer is that we want to have efficiency, linear time algorithm. So the first rule of WCP says that if you have two critical sections that contain conflicting events, then order the two critical sections by ordering the release of the first to the second conflicting event and not to the acquire. The second rule is again on a similar principle, which says that if you have two critical sections that you have inductively confirmed that they cannot be reordered in some sense, which means inductively there is a WCP edge between these two critical sections. So these could be arbitrary events E1 and E2. So if these two critical sections contain events that are already ordered by WCP, then you have to order the first critical sections before the second by ordering the release of the first to the release of the second. Okay, so that is the second sort of inductive rule of WCP. And the third rule of WCP is sort of a way to ensure soundness. It says that WCP is closed under composition with HP. Okay, so what this means is that if you have E1, E2 which are ordered by HP and E2, E3 which are ordered by WCP, then E1 to E3 is a WCP edge. Likewise, if you order E1, E2 from using WCP and E2, E3 using HP, then again E1 and E3 are ordered by WCP. Okay, so this third rule is this composition rule which gives you soundness. It ensures that there are no false positives. And finally, this partial order is the union of the strict order that we define using these three rules with the thread order. Okay, so WCP is defined as in HP. It is given by these three rules, and these rules tell you that you do not have to order all conflicting critical sections. You have to order them only when they have these conflicting events or they're inductively already ordered because of events in them. So with that, let's look at the soundness guarantee of WCP. Okay, as with HB, you can define a WCP race to be a pair of conflicting events, E1, E2, such that they're not ordered by this WCP partial order that we defined previously, either way. So neither E1 is ordered before E2 according to WCP, nor E2 is ordered before E1 according to WCP. So that's a WCP race. And the soundness guarantee says that if your execution sigma has a WCP race, then that execution can be reordered to either expose a data race or a deadlock. Okay. So I want to say a few things here. Well, it took us a while to come up with the soundness proof of WCP, meaning that the soundness proof is really challenging. In fact, there was a precursor version of WCP called CP, causally precedes, which was sort of very similar to this, except that it could not be implemented in linear time. So that order CP, if the proof was broken for CP, and in fact, they also the authors of CP also say that it was a multi-year effort for them to come up with the proof, because you have to reason about reorderings, and that can be very challenging. So the proof of WCP soundness uh, is hard, um, and it also assumes that you have what is called nested locking. So I will not go into the details of all that, but let's move on and let's look at how WCP compares with HP. Okay. Um, the bottom line is WCP is more predictive than HP. Well, this is because WCP is a weaker order than HP, meaning it places fewer edges in the same execution as compared to HP. Or in other words, it has more intuitively linearizations, or it has more pairs of events that are unordered than HP, and therefore, you know, in fact every HB race is also WCP race, which means that if HB can detect a race, then WCP can also detect a data race. So it's more powerful. In fact, it is strictly more powerful. There are examples where HB misses a race, but WCP does not. So let's look at this example here. This is an example that we've been looking at for a long time now. This has two threads, T1 and T2. And these are the two events that are in a predictable data race, but happens before orders them because it naively orders these two critical sections. But WCP does not have this ordering. Okay, the rule 1 says that you have to order critical sections only when they have conflicting events. Otherwise, you should not order critical sections. So WCP will not order these two critical sections, and therefore WCP will not order E1 and E6. So that is a WCP race. So WCP in fact detects this data race, but HP does not detect this data race. So here is another example which is slightly more involved, of that illustrates that WCP has a better predictive power. Okay, so here again you have two critical sections, one containing right of X and the other containing read of Y, and also right of X. So these two critical sections have conflicting events. And as you can see, happens before will order these two critical sections because they're on the same lock. WCP will also order these critical sections because they have conflicting events. But instead of placing the edge from release to acquire, it places this edge from release to this right of X. Okay, so WCP is very careful in how it places edges, and therefore it does not order this right of Y before this read of Y. Okay, although this right of X is ordered before this right of X, this right of Y is not ordered before this read of Y according to WCP. But HB, of course, orders these events. So WCP does not orders these events, and it detects this data race between write Y and read Y. In fact, as you can see, it is indeed a data race because you can first schedule acquire of L, and then you can do, and then both write Y and the read Y are enabled after that point. So this is a more involved example that tells you how WCP carefully adds orderings and exposes very subtle data races like this one. Finally, WCP is also sound, meaning it is very careful in ensuring that if critical sections are not cannot be reordered, then if there is no data race, then WCP should not call that a data race. So here, HP of course will order release before the acquire, and WCP will order the first release before the second conflicting event. So write X and read X are conflicting. Therefore, WCP will place an edge from release to acquire, or release to read of X. So as you can see, both read X and write X are ordered before this read X and write X here. So there is no WCP race, which is in fact as expected because WCP is sound because there is no predictable data race here. Okay, so with that, let me talk about a bit. Let me talk a bit about how to detect data races using WCP. So the WCP is a partial order that we've seen so far, And we have also seen what is the condition for detecting data races using WCP. That condition can be implemented using a vector clock algorithm just like HP, except that there is a slight modification to that algorithm, and it in fact now uses FIFO data structures in addition to vector clocks. And as with HP, it can be implemented in a one-pass streaming fashion, and it runs in worst case linear time. It also uses worst case linear space because of these FIFO data structures. But in practice, this memory overhead was observed to be very low. So the bottom line is WCP detects more races than HP, and yet it runs in linear times as in HP. So in some sense, it is better than HP. We implemented this algorithm in our open source tool called Rapid. So you can go to this link and look at this Rapid framework for dynamic analysis. We evaluated WCP on some standard benchmark suite containing about 18 benchmark programs from the Capo or Java Grande framework. And we looked at executions of each of these benchmark programs, and these executions were ranging all the way from 50 events to about 200 million events. And we observed that WCP scales linearly as in HP, and in fact that the overhead is not that large. And we compared WCP not just with HB, but also with a commercial race predictor, which is based on this symbolic enumeration style race prediction using some SMT constraints. It turns out that when you have to have a scalable race prediction technique using SMT solving, you have to do something special. You have to resort to small chunks of your traces, because otherwise it's too large to handle for a SAT solver. And when you do that, you can in fact miss even happens before races. So that is what we observed. We observed that WCP detects the maximum number of races more than HP. In fact, HB detects more races than the SMT solver technique. And on an average, it is only slightly slower than HP, and it is much faster than a more exhaustive technique like SMT solving, as we expected. So that brings us to the end of this segment, and let's go for a 5-minute break, after which Andreas will discuss other interesting aspects of data race prediction. So again, we are monitoring both Zoom and Cloudr for questions, and also you can raise your hand if you want to ask a question on Zoom.
Umang, you have a question in the chat of Zoom if you want to take it.
Okay, Jens has a question. Those additional 8 data races, any false positives? Well, they were not. In fact, so here in general, it is hard to check for data races because the space of correct. It is hard to check for false positives because you have to look for all correct reorderings. But thankfully, we had access to this SMT solving, and it turns out that all these 8 data races that were extra were in fact also reported by this SMT solving based technique. So that was a nice way to confirm that all of these extra things were not false positives. They were real predictable data races. So that should perhaps answer Jens's question.
All right, so as we are kind of running late on time, should I take over, Umang?
Yeah, sure.
If there are any other questions, I mean, we can also continue the discussion afterwards.
Yes, and I will be monitoring both the Clouder as well as Zoom. So even if you have questions from whatever we've already seen, feel free to ask questions in the chat. Also, it is live streamed on YouTube, and much of the materials are also posted on the POPL website for this tutorial. So with that, I'll pass the baton to Andreas. So let me unshare my screen. Stop share. Okay.
All right, so let me take over. Hopefully you can see my screen now.
Yes.
Is that the case? Okay. Okay, so let's.
Andreas, is there a way that you can make your PDF look bigger to cover the entire thing?
Look bigger. Let me see.
Okay, this is fine. If that's, are you planning to use Adobe? If so, that might be better.
So let me move it. Does it look bigger now?
No, it looks smaller. In fact, it also has a sidebar.
Really? Doesn't show sidebar here. Maybe
you're sharing the wrong screen.
So it should say fundamentals, right? No, the screen is the right one. And it kind of fits the margins of my screen. So let me,
okay, I think
let me start from here.
Yeah, sure.
Okay, good. Okay, so let me take over now. We're running a bit late on time, so I'll try to rush a bit on some parts that might be less interesting, but you can pause and ask questions, so don't let that intimidate you. So in this part, we're going into the more fundamentals of dynamic race prediction. So we're asking the question, well, what is the actual cost of a sound and complete algorithm for this problem? Right. So, oops. I actually have to zoom out. Right. So if we look at approaches so far, for sound and complete race prediction, where these are approaches that take exponential time, as Umang said in the beginning, as they perform a search over the exponentially large space of correct reorderings. And this search can be explicit, just enumerate all possible correct reorderings, or it can be symbolic, relying on some NP oracle like SAT and SMT. So the first obvious question here, which remained unanswered for a surprisingly long time, is what is the complexity of the problem? Is exponential time always necessary? Right, and to answer this question, we'll take a closer look at the problem. So here we're just fixing an event pair of our input trace, and we're asking the question, well, is this event pair E1 and E2 in a predictable data race? And now we are tasked to expose this data race by producing a correct reordering in which these two events, E1 and E2, are enabled in their respective threads, right? But a closer look into how we may answer this question reveals an intermediate step that we have to kind of solve, which is in fact choose the set of events. This is going to be a subset of the events of the initial trace. And then in a second step, choose the right reordering of these events that will turn this, this event set into a proper trace that reports the data race. So this intermediate step is a slice of our input trace over which we then decide the reordering, right? And our search for a witness is a search that can be broken down in these two successive parts, right? What is your event set and what is the ordering on this event set? So, if you combine the two, then you can think of the decision procedure on deciding whether E1 and E2 is a predictable data race of your input trace sigma as a two-step process where at the top level, you iterate over the possible subsets of events of your input trace. Right? And every time you fix one of them, call it X, and then you try to decide whether you can actually order X to produce a valid witness that, manifests the data race. Now, if you fail with some particular X, then you go back, you choose some other event set and so on. until you run out of event sets, at which point you report that you have found no data race between E1 and E2. And now, if you want to deduce the complexity of the problem, well, you can express it as a factor as a product of two factors, alpha times beta, where alpha is the number of choices that you have up here. How many event subsets do you have to iterate over? And beta is the complexity of deciding whether you can linearize any particular set of events to a valid trace. Right. So here we're gonna sketch some bounds on these two factors, alpha and beta. So let's start with the choosing the event subset. So if you have a trace of n events, right? In general, you have 2 to the n possible subsets, right? Every event can either be or not be in a particular subset. So this gives you 2 to the n choices naively. But recall that due to our definition of correct reorderings, we're looking into downwards closed sets with respect to the thread order, right? And what this means is that if I take this red event now in my event set, I have to take all its local predecessors also in my event set. Otherwise, I'm already violating the definition of a correct reordering, right? So this means that in general, my choice of the event set is a choice of how far should I execute every thread. And overall, this gives you a typically smaller bound of n to the t, as opposed to 2 to the n. So, this is again exponential when the number of threads is large, but in most cases, the number of threads is much smaller than the number of events, in which case you're dealing with something that is of order of polynomial, albeit a large polynomial. Now, once you have chosen such an event set X, you need to decide whether you can linearize it to a witness trace. And there is a technical challenge that you have to solve, on your way there, which is that of what we call the realizability of reads from posits. So just to give you an idea, a reads from posit, or we also call it an RF posit, is a simple structure. You have an event set X. This is the set of events that you chose in the previous step. And P is a partial order over this event set that includes the thread and reads from order. And this reads from function is just a function that tells you what write every read should observe, right? And the natural question here is, well, can I linearize my partial order into a trace sigma star such that the reads from function of my trace is exactly what the reads from function of my input is, right? And again, in pictures here we have a set of events. We have a partial order that contains the thread order. And we also have some cross-thread orderings like these two write events here. And we have this reads from function that tells us, for example, that this read down here should observe this write up here. Right. So this is our input, right? This is our RF posit. And we have to produce a linearization of this partial order that also respects the reads from function. For example, in this linearization here, this read observes this write, and then this is exactly what we had to do according to the reads from function, right? So every choice of an event set will yield such a problem of RF posit realizability. And again, in the computational question is, well, how fast can you solve this problem? And without giving you any details, it turns out that you can solve this problem in time t times n to the t. And now, if we combine these two bounds, we get that dynamic data race prediction can be solved in time order t times n to the 2t, where again, just to refresh your memory, n is the number of events and t is the number of threads, right? And to map this into our decision procedure from earlier, what we have just argued is that when you iterate over possible event subsets, you only have n to the t choices to make. And for each one of them, you have to solve the corresponding realizability problem, which can be solved in time t times n to the t. So the product of the two will give you this bound up here. So a moment's reflection here will tell you that sure, the bound is exponential again when the number of threads is large, but if t is something small like 10 or 20, you can think of it as a big polynomial. Right. So in other words, exponential time is not always necessary when you have a bounded number of threads. The data race prediction problem is in polynomial time. Now, the next ambition here could be to see whether you can have something better. For example, an algorithm that is purely polynomial in n, or maybe an algorithm that does have some exponentiation in the number of threads, but at least you're exponentiating a constant and not just the number of events, which is typically a huge number. It turns out that there is a lower bound for the problem, and you cannot do essentially any better. So one can show that DataRace prediction is W1 hard parameterized by the number of threads. So what this tells you formally is that the problem is NP hard when the number of threads is unrestricted, and also you are very unlikely to eat up the dependence of the exponent of n on t. So somewhat loosely, we can say that the upper bound we had from the previous slide is a bound that is in some sense tight, in the sense that you won't be able to eat up this exponent completely on the number of threads. So this gives you a characterization of the complexity of the problem in the general case. Next, we ask whether there are other meaningful parameterizations that might make the problem more tractable. Arguably, n to the 2t might be still a large cost to pay. And now the parameterizations we're going to make are based on the communication topology of the underlying system. And so by communication topology here, I'm thinking of a simple undirected graph, G, where the node set is a set of threads. And I have an edge between two threads if they communicate over some shared variable or lock. For example, here I have an edge between T1 and T2 because I found the global variable X, which is accessed by both T1 and T2, right? And now I will focus on acyclic topologies. So these, prominent examples of these in concurrency are when you have a server communicating with multiple clients, when you have pipelines, or topologies that you get out of divide and conquer parallelism. So this will yield essentially trees, so no cycles. And the task here is to show that when you do DataRace prediction over these topologies, you can actually solve the problem much faster than the general case. Right? And on our way there, we just need basically one technical definition here, which is that of closure of RF posets. So recall our definition of RF posets from earlier, a set, a partial order, and a read from function. And now we're going to call an RF poset closed if it satisfies two conditions. Right? And these conditions can be very well illustrated in pictures. The first condition says that, well, if you have a read, and this read is supposed to read from some write up here. Now, suppose you also have another conflicting write that is ordered before the read, then you have to order the write also before the observation of the read. Right? And this is like an ordering that is necessary, meaning that any linearization of your partial order that respects the observation function has to actually order the write here before what the read is supposed to observe. Right. And in the middle, we have a completely symmetric case. If the observation of a read is ordered before a conflicting write, then you also have to play the read before the write, so that this write does not get stuck in between and alter the observation of the read. And the second condition is a completely analogous condition phrased on critical sections. And it tells you that, well, if you have two critical sections on the same lock, and the acquire of the first is ordered before the release of the second, then the release of the first has to also be ordered before the acquire of the second. Again, this is a necessary ordering in order to not have overlapping critical sections that would violate lock semantics naturally. Right. So, if these conditions are met, your poset is called closed. If they're not met, then you can try to compute, a minimal strengthening of the poset that will satisfy these conditions. And that's what we call the closure of an RF poset. And again, the question we keep asking in this section, how fast can you compute this closure? Right. So it turns out that the closure of an RF poset can be computed in this amount of time, t squared times v times n squared log n. The new parameter here is v, which is the number of locks and variables that you have. So, on your way to strengthening your partial order as you compute this closure, two things can happen. On the one hand, you might create a cycle, so you're no longer dealing with a partial order. And at this point, you can stop and conclude that the RF poset is not realizable, meaning that you're guaranteed to not have a linearization of the partial order that will also respect the read from function. Or, so, in some sense, the existence of the closure is a necessary condition for the realizability of the RF poset. On the other hand, you might, conclude your computation without encountering a cycle. At this point, the RF poset may or may not be realizable, but one can show that realizability can be guaranteed in this case if you also have some extra side conditions. right? And one of these side conditions one can show to be dealing with acyclic topologies, right? So in other words, when you're dealing with acyclic topologies, the existence of a closure of an RF poset is both a necessary and a sufficient condition for its realizability, right? So then we can take this this result now and plug it into a new DataRace detection algorithm for acyclic topologies, and in fact solve the problem in time t squared times v times n squared log n, where this is a natural notation for our parameters. And notice here that we have no exponential dependence on any parameter, as opposed to the general case. So we're at most, raising to a power of 2. And again, to map this into our diffusion procedure from earlier, acyclicity of the communication topology allows you to prove that, well, it suffices just to examine a single event set and the realizability of the corresponding RF poset. And then, deciding this realizability amounts to computing the closure of this RF poset, which we just argued can be done in this amount of time. Right. So at this point, you have an algorithm that, it's essentially quadratic as far as the dependence on n is concerned, which is typically by far the largest parameter of the input. So again, if you're overly ambitious, you might ask, well, let's try to do something better. Let's try to break below this quadratic bound on n. Right? Is there an algorithm for that? Unfortunately, it turns out that no. In fact, dynamic data race prediction, even over simple traces that consist of only 2 threads and have 8 variables in just a single lock, have a hard quadratic lower bound, at least as far as polynomial improvements go. So you're very unlikely to have an algorithm, for example, that operates in time n square root n. I mean, this would violate popular hypothesis in complexity theory. And so if you now, take this lower bound and plug it into and combine it with our previous upper bound, you get that the upper bound that we have is again optimal, at least as far as polynomial improvements are concerned, when you take, the number of threads and the number of variables to be reasonably small, of the order of polylog, as far as the dependence on the number of events goes. So this concludes this part of the talk with a nice little summary where we examine the complexity of the dynamic data race prediction in general setting, and when we have acyclic topologies, and in both cases we have some upper bounds and some lower bounds that are in some sense matching. So from this perspective, there's not much room for further improvements. So let me stop here and see if you have any questions before we proceed to the last part.
So for the people in the Zoom meeting who are also interested in the weak memory literature in concurrency, Andreas, if you go to slide 49. So there, Andreas has a RF poset, and the closure essentially tells you that the from reads mapping or the reads before mapping is also included in this RF poset. Yeah.
Right. Okay, so let me proceed then with the last part. Again, you can also ask questions afterwards or reach out and discuss further. We're very open to that. So this last part is about M2. M2 is a data race detector that is sound on polynomial time, and it's based on some insights from the theory of the previous section. So I phrased the question of finding the right witness for a data race as a search for the right event set and the search for the right ordering over that event set. So here I'll just give you a flavor of how M2 performs each of these choices. Now, as far as the choosing of the event set goes, M2 is following a very simple heuristic, which says, well, just proactively close all critical sections that do not contain the two events over which you're deciding a data race. So M2 will construct a set X where three simple principles have to be met. The first is that we have to take in X all the local predecessors of the two events in their respective threads. The second condition says that X has to be closed with respect to these threads and reads from order. And the third one is this heuristic on top, which says that you shouldn't have any open critical sections except possibly those that contain E1 and E2. So in pictures, we do as follows. We have our input trace here. We have these two little events, E1 and E2, and we need to decide whether they are in a data race. So M2 will initially take these grayed events in our event set. This is due to condition 1. At this point, we have this read event down here, so we have to take the write event up here, also in our event set, and its respective predecessors. So we will increase our event sets. And at this point, we have two critical sections open on this log L, one starting up here and the other starting down here. Now, the first one contains this event E1, so we're not going to touch it. But the second one doesn't contain any of the two events. So, the third condition says that you should close that. Right? So now the grayed events mark the choice for the event set X, and we only have one choice to make. Now, at this point, if either of the two events has become part of the set X, then we stop and we report no race. Otherwise, we will take this X and we will proceed with the second part. We will try to linearize it to produce a witness for the data race. So let's see how the construction of this linearization goes. If you recall our solution from the previous section on the RF posit realizability for acyclic topologies, then we saw that when you compute the closure of an RF posit, if you don't have a cycle, then it may or may not be realizable, and you can throw in some extra conditions that make it realizable. In the previous sections, the condition was dealing with an acyclic topology. Now, M2 is a data race predictor that deals with arbitrary topologies, so we cannot use that. So let me just give you what this new extra condition is the one that M2 relies on. So this condition is something we call max-min, and the corresponding theorem that enables this condition is the max-min theorem. And basically, this theorem says that if you have a closed RF posit where you can further partition your event set X into two events sets Y1 and Y2, where Y1 is totally ordered and Y2 does not have to be totally ordered, but it has to order all pairs of conflicting write events, then you're guaranteed that your RF posit is realizable. Right? So the conditions still allow for conflicting events to be unordered as long as they sit on opposite sides of these two event sets in the partitioning. For example, down here, we have Y1 up here, Y2 on the right. We have these two write events, and they are unordered, but still the conditions of the theorem are satisfied. So whenever you satisfy these two conditions, then you're guaranteed that there exists a linearization of this RF posit that will actually produce a valid trace, and therefore you can conclude its realizability. And now this is directly used by M2. So the algorithm, when you try to decide for a data race between E1 and E2, the algorithm initially will construct an event set and the corresponding RF posit as it's shown here on the right. So these two E1 and E2 events are the ones that are enabled in their respective threads, and we're trying to execute them concurrently. So M2 will construct this RF posit on the right, where we will order every read event before and after the write event that it's supposed to observe. So for example, here we have this read event. It's supposed to observe this write event up here. We have this blue ordering between them. And moreover, we have an open critical section here on L, which means that we have to order this acquired after every other release event on the same critical section. Right. And the next step for M2 is to compute the closure of this RF posit. So here we have this write event here transitively ordered before this write event on the left. So the rules of closure tells us that we have to insert a new ordering from the read event to this conflicting write event. At this point, we're done. So next, M2 will try to create the conditions for the max-min theorem, and this will be done by simply partitioning the event set into two Y1 will take all the events of a single thread. So these are naturally totally ordered. Y2 will be the set of all remaining events. At this point, the conditions of the theorem are not met because, for example, we have a write event up here, which is supposed to be observed by this read event. And we have another conflicting write event on Y also here, and the two are unordered. So at this point, M2 will just guess an ordering between them, and the guess it will make is, well, order them in the same way as in the input trace. Right? So it will insert this ordering kind of arbitrarily, and we'll now we have a new RF posit, so we will compute the closure of this RF posit again by inserting this new edge, now pushing this conflicting write event below the read event. And at this point, we're done, actually. The conditions of the theorem are satisfied. So Max-Min theorem tells us that since we haven't encountered a cycle in this construction, the RF posit is, in fact, realizable, and we can linearize it to a valid trace. So, overall, M2 took as input the trace on the left, and it produced a correct reordering that exposes E1 and E2 as a data race. And more generally, the guarantees that M2 has is that it will always make sound predictions of data races, and the overall complexity is pretty much quartic on N. And when you have two threads, then you're also guaranteed completeness. So, all possible data races are going to be reported. Now, I won't talk much about experiments. I'll just show you a few numbers here where we compared M2 against other data race detection techniques. Some of them Umang talked about earlier. Here we have some variants, not exactly what Umang presented, to ensure soundness on all reports. And what we found is that M2 basically detects every data race detected by any other method. And there are quite a few cases where it detects more. So, down here, we have quite a few data races that were only detected by M2 and missed by every other method. Now, all these methods operate in linear time. M2 fortunately operates in polynomial time, but it's a higher polynomial, so this is reflected somewhat in running time. So compared, for example, to SHB, M2 was somewhat slower. But one might argue that this slowdown is something that you might be willing to pay if you want to have a higher coverage, as M2 seems to have. Now, before pausing for questions, let me conclude real quick. I see we're running late on time. So this is a wrap-up of what this tutorial has been about. Umang showed you this nice picture earlier with the spectrum between exhaustive techniques that are sound and complete, and very efficient techniques that are typically incomplete, like happens before. And this tutorial was about a few data race prediction techniques that try to balance the best of the two worlds, either with linear time guarantees or polynomial time guarantees, but in each case with higher predictive power and always sound. So there are other works. I mean, this is a very actively studied topic, and we didn't have time to cover everything. I'll just mention here a few other approaches to dynamic data race prediction based on partial orders. Unfortunately, all these techniques are not only incomplete, but also unsound. So soundness is a very tricky task to get correctly, as Umang mentioned in his part. And let me quickly also conclude with a few other challenges that we have identified in the area. The most obvious challenge to us is to have a data race predictor that is always sound, operates in linear time, and is as precise as possible. This is a guarantee that this triplet here is something that you want to have, especially when you deal with runtime verification, where you don't have much time to perform data race prediction, right? And some progress has been made, but this we're still not where we would like to be, at least as far as precision goes. Another challenge is to relax the notion of witnesses and correct reorderings. As Paros mentioned earlier, maybe one wants to relax the notion of the reads from function to also allow reads to observe different writes, as long as they write the same value, or maybe you can rely on some static information to increase precision and go to more efficient techniques. I think this also poses some challenges on the technical challenges on the tools that perform the monitoring of the corresponding program. If you want to, also record values and not just the type of the events that you see. Of course, we talk about data races, but there are other concurrency violations that we would like to detect, like deadlocks and atomicity violations. And of course, there is work being done, very nice work being done these days on all of these, but to our understanding, it's nowhere as extensive as DataRace is. So hopefully we can transfer some of our insights from DataRaces to these other domains. Going further, relaxed memory models. Yes, Umang is something, Umang also mentioned this a couple of times. With relaxed memory, you can allow more reorderings. So the challenge of producing the right reordering that exposes the data races might become even more difficult. But still, this is a challenge that it's very hot nowadays, and for practical reasons, it's something that we can't ignore as a research community. Another important direction, in my perspective, is when we deal with concurrent programs that mix communication primitives, like, for example, in the Go language, it's very common to have communication over both shared memory and message passing, or maybe you have communication over some other concurrent data structures like stacks. And then, you need to redefine the notion of a correct reordering, and you need to rethink about a good algorithm that finds these correct reorderings. And lastly, we need benchmarks. I mean, we have some standard benchmark sheets that we keep up using for our benchmarks, but it would be nice to have a few more, especially when it comes to expanding the research to these other areas where relaxed memory or mixing paradigms. So this brings us to the end of the talk. I won't spend time here on this last slide. This is a small teaser of an upcoming POPL talk that we have on something called synchronization preserving races. This is a new notion of data races that we explore in this paper, both in terms of practical coverage and also computational complexity. So I won't say anything further here. I'll just invite you to watch the talk and tune in on the Q&A session on Thursday if you want to discuss on that more. So thank you. Thank you, everyone. Let me know if you have any questions. Yes, I think Ori had
Okay. We have one question on CloudR, which is on how much slower on average a program is after being instrumented to generate these traces. Would it be feasible to generate traces in production? So that's a good question. So, yeah,
that's a good question that Umang, you might be more capable to answer.
Sure. So if you look at trace detection and when you have to instrument memory, depending upon how precise you are in your instrumentation, typical tools like thread sanitizer, which are in fact the gold standard for industry, they incur a slowdown of 5 to 10x. Okay, there are certain techniques that let you sample and reduce this sample what you want to instrument, and that may lead to a lower memory overhead. But typically, both memory and runtime overhead can be large. Okay, so I see a question from Parosh. She has raised a hand, and you said Ori also had a question.
Sure. So Paras, why don't you go ahead?
Okay. So related to what you mentioned in the end about relaxed memory models, in fact, data race freedom is used as a notion of correctness for programs running on such memory models. In the sense that if you, for some memory models, if you guarantee data race freedom when you run the program according to the SC semantics, then somehow you show that the program will have the same behavior when you run it on the relaxed memory model. So my question is twofold. First of all, how can you tune your techniques to be able to have efficient ways to guarantee that programs' behaviors are the same under the given memory model and SC? And second, whether you can also use your techniques, which I think is interesting, to analyze other notions of correctness, like, for instance, robust behaviors. This is like a refined notion of data race freedom that also guarantees correctness of behaviors of programs running on such memory models. So if I summarize my question, whether you can tune your techniques to be more efficient in that context, and whether you can adapt it to other notions of correctness in that context. Thank you.
Sure. So I can only speak from a complexity theoretic point of view now, because if one wants to have a practical statement, one needs to test, and I don't have the capacity to do this now. When it comes to relaxed memory models, I'm fairly certain that some of the, at least, techniques for understanding the complexity of the problem transfer when you go to TSO and PSO. So, this is a first step into applying these techniques to these models, or at least,
yes,
figuring out whether new data races arise that are absent in under SC. Now, for other more complicated memory models, I can't give you, an informed opinion, but this is something that very much interests me.
But I mean, even in the context of TSO, what would it mean to have a data race there? I mean, it's not because the writes are not atomic. So does it mean that? So what would it mean to have a data race there? Is it the same definition, or do you need to adapt the definition of a data race in the first place?
Right. So they're not atomic, but in principle, you could try to see whether the memory counterpart of two writes might happen concurrently. So at least the write-write race might be easier to define. I'm not sure about the read-write race.
I mean, there are some issues that can be subtle there, but it's interesting. Yeah. Okay. Thank you.
Yeah.
I understand.
Yeah. Thank you.
Very
much. Any other question? All right. Let's wrap up here then. Thank you everyone for attending. The material is going to be online, as Umank mentioned, and if you want to reach out at a later point and discuss or ask, we're always happy. Have a good evening, afternoon, or whatever your time zone is.
Thank you. So we have some questions.
Oh, we do.
No. In the edition, no, okay, we don't. So yeah, I think it's safe to quit the Zoom.
Yeah, I think I have to release the ACM account here, but I will be online on Clouder with my personal account and see.